Hello and welcome to Veteran Physics. Today I'm going to be talking about vectors. This concept is going to be, I'm going to break it up into two videos. The first video I'm going to talk about vector addition and vector components, and the second video I'm going to be talking about unit vectors and vector products. So let's jump right into this. First things first, we need to know what is a vector. Well, a vector is both a magnitude and a direction. And I have an example of a vector here. So this vector v that I've named it happens to be 6 meters long, and it's in the direction of 40 degrees from the x-axis. A little bit about the anatomy of the vector. The end of the vector is known as the tip of the vector, or the head of the vector, and the beginning of the vector is known as the tail of the vector. Vector is also displacement. So if we're going, and a displacement is a change in position. So if we're going from point A to point B, so the displacement to go from point A to B is represented by this vector that I've created, vector v. And so therefore point B minus point A is equal to vector v. The way that we note vectors on paper is the letter or symbol that you choose for your vector with a little arrow on top, and that will represent a vector on paper. Now if we had a vector anywhere else on this graph, I have one right here. If it's in the same direction anywhere else on the graph, then vector v is going to be parallel to this vector that I created. Now if this vector that I created also has the same distance or the same magnitude and direction, then this vector, let's name it A, is equal to vector v. Likewise, if there's a vector anywhere on the graph and it's going the exact opposite direction, then it's going to be anti-parallel to vector v. And if it's opposite direction but the same magnitude as well, then it's going to be the negative equality. So we're going to have vector v, let's call this one v, is equal to negative vector b, and positive vector v is equal to negative vector v. Now if we want to talk about just the magnitude of the vector, then we're going to put in absolute value. So the absolute value of vector v, or the magnitude of vector v, is 6 meters. Okay, so now we know what a vector is, we know the anatomy. Now let's actually do some addition. So vector addition is both associative and commutative. First, let's do this graphically. So say I wanted to go from point 1 to point 2. The way that I've noted here, there may be more ways or less in terms of how I can get to point 1 to point 2. Here I've noted I can get to point 1 to point 2 if I follow along vector A. And this is important, vector A's tip is connected to vector B's tail. So this is an addition as opposed to subtraction. So if I go vector A plus vector D, then we're going to go from point 1 to point 2. But we could also get from point 1 to point 2 if we go along vector C. So if P2 minus P1 is equal to A plus B, and P2 minus P1 is also vector C, surely vector C is equal to A plus B, and that's exactly what it is. Here's a more complicated version of this. So I'm going from point 1 to point 2. There are several ways that I can take. I could follow A, which is continued by B, which is continued by C, but A plus B is equal to vector D. So I can go from point 1, follow along vector D, and then go up to vector C. But D plus C is equal to vector F. So if I want to get from point 1 to point 2, I could follow vector F. And here we have the equality A plus B plus C equals D plus C equals F. And like I said, it is commutative. So let's just look at this triangle here. We have A, B, and D. If A plus B equals D, then surely D minus A equals B, D minus B equals A minus D equals negative B, and B minus D equals negative A. And that's exactly what it is. And we can see this graphically too. So we start at point 1 and we follow along D, and we want to go along B. Well, you can see that the tip of B is connected to the tip of D. So we're not going to add B to D, we're going to subtract it. So we go along vector D, we subtract vector B, and we're going to get vector A. Likewise, if we go along D, the tail of D is touching the tail of A, so D minus A is going to be B. The last thing I want to talk about for this portion is going to be the amplitude, or the scalar of a vector. So take this vector that I made, vector V. Well, if we multiply it by 2, it's going to be the vector in the same direction. It's not, the ratio of the scale is not very good. But it's going to be the same direction, but twice the magnitude. So this right here is going to be 2. Alright, so now I'm going to talk about vector components. Okay, so vector components. What are vector components? Well, a vector typically travels in one or more directions. If we're looking at a plane, a vector travels in both the x direction and the y direction. The components are the distances that that vector travels in any one direction. I have an example here. For this example, I've created vector v, and vector v has components v of x and v of y. V of x is the distance that vector v travels in the x direction, and v of y is the distance that vector v travels in the y direction. The components are also known as the projections of vector v. If you remember the vector addition, we have a similar situation here. We're going from this one point to another, and we can go two ways. So vector v plus v prime is equal to vector q. Likewise, we can add components. The component of vector v in the x direction plus the component of vector v prime in the x direction is equal to the component in the x direction of q. Likewise, we have v of y plus v prime of y, and it's equal to component q of y. But say we wanted the magnitude of q. Well, we can put q and its components into a triangle. The hypotenuse would be vector q. Theta would be the direction that vector q is traveling from an axis. Q of x would be the adjacent, and q of y would be the opposite. If you've forgotten some of your trig rules, I've written some of them here. Q of y over the magnitude of q is sine theta. Q of x over the magnitude of q is equal to cosine theta. And q of y over q of x is equal to tan theta. But most importantly, the magnitude of q can be solved using Pythagorean theorem. So, the magnitude of q is equal to the square root of q of x squared plus q of y squared. It is important to know, however, that components are not vectors. The last thing I want to talk about is multidimensional vectors. Here I have an example of a vector that travels in three directions. Vector n travels in the x direction, the y direction, and the z direction. And so we would calculate the magnitude by using Pythagorean theorem, and we would do the square root of n of x squared plus n of y squared plus n of z squared. If it traveled in more than three directions, then you would add it up all the way to n of n squared directions. In any case, this has been part 1 for the vectors concept. Hope to see you in part 2.